Atomic nuclei must have structure. The structure is what determines their properties. The structure is unique for every nucleus. So given some A and Z, you have this structure or that structure. And it is built on the basis of smaller structures. Specifically, alpha and deuteron are the main ones. And the clusters thereof.
Greetings, this is Eugene the Philosopher, the greatest living philosopher after the unfortunate passing of Quentin Robert de Nameland, who has been the greatest living philosopher before me. So I promised to give you Burtaev's theory of, or rather phenomenology of atomic nuclei, and without further ado, let's look at it.
Well, to begin with, I recommend you to review or watch for the first time, if you haven't, my video Phenomenology of Elementary Particles. That is this one. That I've posted relatively recently. At least if you're watching this on Patreon. If you're on YouTube, that would be quite a while ago. Anyway, so in this video, I describe the phenomenology of Burtaev regarding the particles themselves, such as protons and neutrons, which would interest us in this particular case, since we're dealing with atomic nucleus, which is built from them, all right? And this model that he has for these particles, it's not just, some sort of insight or whatever. It's based on specific experiments of, for example, Hofstadter, Kendall, Friedman, and Taylor. You can see these guys got Nobel Prizes in 61 and 1990. So apparently they did something useful. In particular, these guys that I've mentioned have used this electron scattering to figure out the structure of nucleons. And later, Steinberger and Lederman and Schwartz, who also got Nobel Prize, have used neutrino scattering. So, and got basically the same picture. So what should it tell us is that this model is correct in air quotes, at least it corresponds to something in reality. And anyone who builds a picture, a model of a proton or a neutron must have similar results in the end, because again, these are experimental results. So Burtaev's theory, or model rather, corresponds to these experiments, like it fits, okay? And in this model, we have in every nucleon, such as proton or neutron, we have a core where you can say it's roughly 6 pi-mesons, each having a mass of roughly 140 or 135 MeV. Oh, I'm sorry, that would be a muon. Never mind the masses. Let's just say 6 pions, and so the core is relatively small, and then we have a relatively big fur coat with 1 pion. And why is it bigger? Well, it's because the mass is lower. Again, the smaller energy / mass a particle has, the bigger size it would have. So again, almost as if something like a density was constant, right? Actually, it's more like a mass is constant. Therefore, the smaller size, the smaller volume, the bigger density, and vice versa. But never mind. So 1 pion would be that would be 4 feathers of Burtaev. That would be roughly 4 times 35 MeV. Actually, slightly less in case of nucleons, 33.5. And you get the proper readings, okay, and the proper sizes. So that was just the introduction, okay. I was just repeating. Again, you can see this video to get more details, all right. Once we get into the nuclear sector, so to speak, like we start building some structures out of these nucleons, all right. And let me describe you the model of Burtaev, his phenomenology of atomic nuclei in a nutshell, okay? Let me try. So first of all, the cores, these dense inner parts of protons and neutrons, we shall consider them basically constant, okay? Meaning they aren't interfered with, they aren't distorted by, I guess, the so-called nuclear interaction. We shall talk about this in a minute. But only the fur coats are, okay? So only these bigger outer parts, for the lack of a better word, participate in what we call nuclear interaction, okay? That's kind of, I guess, an assumption, but it's a very reasonable one, I guess. I mean, since this thing is so small, like 6 times smaller than the outer layers, then why wouldn't we assume that it doesn't even interact, right? Therefore, protons and neutrons interact through their fur coats only. So this external layer roughly corresponding to one pi-meson. And this interaction is described in this phenomenology. Again, I return to my comment to the previous video where we described Burtaev's phenomenology of particles, where it's based on essentially a hand waving, right? We don't really know, at least I don't really know, what kind of oscillations he talks about. He just vaguely says it's some oscillation of substance, right? And again, I'll return to this point later when we shall conclude, where I say how depressing it is to not being able to precisely determine what is oscillating, etc., etc. But nevertheless, we describe this interaction through mutual arrangements of spins and magnetic moments, okay? So essentially what follows from this, and Burtaev has talked about this in some of the interviews, let's say, and in some of the texts he only vaguely kind of mentions this, but ultimately in his model, in his phenomenology, the nuclear force is essentially a magnetic force. Therefore, there is no strong interaction. I mean, this he definitely says out loud, that there is no such thing as a independent strong nuclear interaction, you know. So there is nothing specific about nucleon interactions, let's say, with respect to interactions within atoms or something like that. It's just that the sizes are different, therefore the phenomena are different, therefore the mutual arrangements, the structural deformations are all different, right? But if you want a substitute, like a mainstream sort of substitute, where we have, like the four interactions of standard model, let's say, then in this case we may say that it is magnetic, okay? But Burtaev not necessarily means it literally, okay? But still, if you want to get the closest force that we know about today, that would be the magnetic force, all right? And there is no strong nuclear force. And here I want to make a couple of comments. So not a lot of people realize this. Usually people only look at the electrostatics, okay? But if you think about it, all of these small particles, even electrons, for example, are small magnets. Like electron has magnetic moment, which means even two electrons would interact magnetically. And I did a little calculation which shows that at distances of about half a picometer, right, 5 times 10 to the minus 13, two electrons, their magnetic force would be the same magnitude as the electric force. So if the electrons are closer than this distance to each other, they can actually attract instead of repel. I mean, that obviously requires some geometrical arrangement, because the magnetic moment depends on the angle, right? It's the electrostatic which is spherically symmetric, but the magnetic force depends on the angle. But if you align electrons properly, then if you bring them closer than this distance, they would start attracting. And in fact, it would be sort of like a runaway attraction effect. They would never repel. They'll actually crash into each other, which is an obvious problem, right? So we have a Coulomb law, which tends to infinity when the range goes to zero. And we have this magnetic attraction, which also tends to infinity when we go to zero. So it's kind of bad for both the Coulomb model and the magnetic model. So this is another hint that these are just approximations, okay? But still, I mean, if you assume that the electron is a point-like particle with a magnetic moment and electric charge, if you bring them closer than this distance, they'll start attracting instead of repelling, again, given the proper alignment geometrically of these magnetic moments. For two protons, it's roughly 7 times 10 to the minus 16, right? But then again, at least in this model, and in let's put it this way, a common sense model where neither a proton nor electron is a point-like particle, these figures are comparable to the sizes of particles themselves. I think for electron it's actually much smaller than the electron itself. I mean, depends what you consider the electron radius, right? And for proton it's roughly the same. Like right now, what is called the proton radius is something like 8.4, I think, times 10 to the minus 16, or about so. But here it's roughly 7, I think. That was my calculation. At this distance, 2 protons will start attracting just magnetically, okay? And again, another comment of mine is that if nuclear force actually existed, then neutron-neutron and proton-proton interaction would have been possible. So things like element 0, and I'm not talking about Mass Effect game, even though I love it, things like element 0 would exist. Actually, another title for it is a dineutron, okay? And it doesn't, all right? Neither does PP structure exist, which sounds funny, I know, but it's a helium-2, right? It's just 2 protons, but they don't. And why is that? Well, there are some absolutely ridiculous explanations from Pauli's exclusion principle. Like people say, well, how can you have this structure with different quantum numbers? Well, easy. 1 spin up, 1 spin down, different quantum numbers. What's the problem? But they don't exist, right? It means that the nuclear force is a scam. It's just not existed. It doesn't exist, sorry. Okay? But anyway, in Burtaev's theory, proton-proton and neutron-neutron interactions don't even happen because the fur coats are identical. And this is a question mark because I'm not sure. Like, he never says this explicitly, but I think this is his idea. He just says that proton interacts only with neutron and neutron interacts only with proton. They don't interact with each other, like proton-proton, neutron-neutron. But he doesn't clarify. I think it's because, again, like, this is our assumption, right? They interact only through fur coats, and they are identical for 2 neutrons and for 2 protons, and therefore they cannot synchronize properly this rotation, which we ascribe the interaction to, right? The spin and magnetic moment, they cannot be aligned properly, all right? Something like that. And one of the crucial points, this is no longer my comment, it's actually what Burtaev requires, is the axial symmetry. So everywhere we'll see axially, roughly, okay, as much as possible, as I wrote it here, roughly like axially symmetric structures. So z-axis would be present everywhere, which you can obviously point anywhere, so it doesn't matter. But the axial symmetry will be there, okay? Then, in his model, or theory, if you wish, the mass defect or binding energy is essentially caused by a change in energy of these fur coats because of their interaction. Because again, because of this postulate, if you wish, okay? So these fur coats deform because of the interaction. And again, what kind of interaction? It's, if you want like a short answer, it's magnetic. If you want a longer answer, it's none of these, you know, usually recognized types of interaction. It's just an interaction of substance with itself, all right? But anyway, this interaction introduces deformation of fur coats, which changes their spatio-temporal characteristics and therefore energy. If you remember how we calculated the mass of pi-meson and the mass of muon based on the mass of electron, we've basically, again, used this conjecture that the smaller size means bigger energy, right? And if the fur coats deform, their size changes, therefore the energy changes, and therefore the total energy will also change. That's the easy answer. And a very important point here is that in Burtaev's model, there is no Coulomb barrier because, again, electric charge is an integral, almost, you might say, topological characteristic, and I'll try to clarify in a second, which is only apparent or visible from far away. And thus, nuclear reactions, fission and fusion, may be much... It's not Burtaev's comment, by the way, this is me saying here, that nuclear reactions must be much easier to achieve and therefore more prominent than we think. So things like... and I know I'm going on a wide, long, far away fringe here, but still I want to say that I believe that transmutations are much more prominent and much more frequent than we think. We just kind of tend to not even think they might be present, but I'm pretty sure they are. But this is purely my comment. So let's return to this idea that the charge is a topological characteristic. What do I mean by that? Well, I mean specifically that we know that the electrostatic interaction is a very long-range one, right? So the particles very far away must know that there's something sitting roughly speaking, here, where the so-called electric charge is positioned. Well, in Burtaev's model, the electric charge is, again, it is determined by the mutual orientation of rotations of this inner and outer parts, or for electron, that would be transverse and longitudinal oscillation, if you wish, okay? So if they rotate in the same direction, it's the positive charge. If they rotate in the opposite direction, it's the negative charge. So this sort of, twist in this area of space is what I call the topological characteristic, okay? So how the space is twisted in a particular point. From afar away, if the twist is transverse, coincides with longitudinal, it would look like a negative charge. As I coincide, then it's positive charge. If they are the opposite rotations, it would look like a negative charge. What we currently do in our, simplified Coulomb approximation, we describe as an electric charge, right? That's the idea, and therefore there is no Coulomb barrier, because again, when you come closer to these structures, like the topology matters not so much as the actual structure, because, it's evident when you're close to them, right? You can observe. This is the so-called near field, like they do it in usual electrodynamics, sorry. This is the near field. Where all of this topology, which can only be seen from far away, doesn't really matter. So there is no electric charge within these particles. It's an integral characteristic which can only be perceived from far away. And therefore, again, I make this conclusion, right? The nuclear reactions must be much easier to achieve than people usually think. So, I would go as far as to say that at this point, you actually need to explain why cold fusion doesn't happen literally everywhere, rather than to explain how it can happen at all. Okay, but that's just my view. That's not what Burtaev would say, probably. What Burtaev would say, though, which I've heard in a couple of interviews of his, is that there are no laws, essentially. What he means by that is that there is no simple relation that we can name a law and use everywhere in nuclear physics. Unfortunately, I have to add. So he says that you basically have to describe all of the multiplicity of nuclei, all of nuclear physics, or rather, you can't describe it with a single rule. Okay, each nucleus is basically unique because it has a unique structure. So one has to go and sort of dig through every separate case. And digging he did. So he has 5 essentially books on nuclear physics. We're gonna skim through them very quickly right now, because again, if you look at it, it's 750 pages total. So that's book number 1, book number 2, book number 3, book number 4, and also the a postscript or whatever, PS, which also 50 pages. So let's take a look at it. So very briefly, again, 750 pages, it would make no sense for us to read it because it would take literally several weeks. So we'll just look at some of the notes I've made and maybe some comments that I'll make right away. So these are the simplest structures that we have. Deuteron, Triton. Once again, all of these books are available. I'm gonna link, but they're in Russian, as you can see. But I'll comment in English, obviously. So we have a deuteron, a triton, that is hydrogen 3, right? And a tritid, that would be a helium 3. So these are linear structures, and essentially, again, the interaction is sort of magnetic in air quotes, okay? So you can say the arrangements of spins and magnetic moments here. And again, it happens due to the deformation of the fur coat. How exactly, is there a simple law to calculate the energy difference? The short answer is no. Unfortunately, there isn't. Like I've looked into it in a lot of detail, because again, the deuteron is probably the most important particle because it is the defining particle for nuclear interaction. But unfortunately, there is no simple law that can describe this interaction. Unfortunately, I have to add for like a 15th time, but it's very unfortunate, yeah. Then we take a look at alpha particle. It's a spatial, like a three-dimensional arrangement of two deuterons, essentially, where we have, well, you can consider it like a dumbbell. So one is in the plane of this picture, and another is like perpendicular, so it goes from me to you, or sorry, from us to the screen, let's put it this way, or vice versa. Well, here it's shown in sort of an isometric projection. But this thing is perpendicular to this thing, and they also are removed to some distance along the z-axis. And you may see that it's an absolutely antisymmetric picture, and therefore alpha particle is incredibly stable. So it doesn't really want anything else. It's perfectly happy as it is, all right? And that's why it's so stable. And all of these four particles are actually pretty stable. So they don't have states with higher mass energy with respect to the base one below their decay energy. So if you pump energy into them, they might rearrange, but they would rather decay, okay, into something else. Which means these are incredibly stable structures, and we shall build everything from these stable structures. In particular, we're actually not going to be using helium-3. We're going to use deuteron, triton, and specifically alpha particle. Actually, again, a brief comment. Alpha particle is probably the most important particle for Burtaev's model. Like, he just puts it everywhere. So it's very similar to what has been named alpha cluster model. So essentially, we're going to be building larger nuclei from clusters of alphas, okay? And here we see these, again, anonymous sort of oscillations, which we discussed in a lot of detail in my previous video, the phenomenology of elementary particles, okay? All right, so no stable isotopes with 5 nucleons exist. I'm just looking at how long will it gonna take, which is caused by extreme stability and symmetry of alpha. So everything with A equals 5 tends to decay into alpha. And here's this comment which I've already made. We also need to consider mutual orientations of spins and magnetic moments when we are constructing higher A nuclei. A is the number of neutrons plus protons combined, in case you are not into nuclear physics, okay? So lithium, beryllium, boron is their extremely low abundance is caused by, again, extreme stability of alpha. So all of these guys, like, they're not really the abundance they should have had has entered alpha, so to speak, okay? So alpha particle is, I think it's the second most, or the third most popular, so to speak, particle in the universe after proton and electron. Just because of its extreme stability, because of this structure that it has, okay? Then we can look at lithium-6. Wait, was it 50? Yeah, so he actually is very honest here. He describes different possibilities. So you can see we already like depict alpha as just a single block. So this is alpha, this is proton or neutron. So these are two possibilities how we can build lithium-6. He describes them in quite a bit of detail, and I don't think he actually concludes which one is the correct one. So there's a very honest discussion about this. Like, he talks about the excited states, he talks about the decays and stuff. But yeah, this is lithium-7. This is kind of the main isotope of lithium, where again we have alpha, then a deuteron, and a neutron glued to them. Or another possibility is alpha, neutron, neutron, proton, right? And I think this one looks more stable, but I'm not sure what Burtaev says here, like which one is the correct one. Like he looks into moments. Actually, like again, it's not just we're concocting something. Again, a general comment. Where are these 750 pages? I'll show you. This is actually like considerations of actual data, like of actual orbital moments, of decay energies, of excited state, things like that. So there's a lot, you know. It's all based on data, essentially. So that's why we do it phenomenologically. We don't have a simple law, but we have a megatons of data, okay? And that's how we concoct these models. By hand, essentially, but taking into account all of the observations. Well, I can show you much more, but it's very, very crazy how many tables of all kinds of stuff there is in these books. Okay, just to get you an idea. That we're not just hand waving, we're actually being informed by all of this. Well, we'll talk about this in a moment, about these blocks that you just saw. Anyway, let's return. We were talking about lithium. Okay, that's pretty far. So that's lithium 6. That would be lithium 7. What else do we have here? Yeah, so honest discussion of various possibilities. This is actually a note for me. Like, maybe additional clues on how are these, roughly speaking, shells, okay? I don't mean what I say, but just for simplicity, how they are being filled. Maybe it can be, maybe you can introduce some simple law, like, you know, following the entropy considerations, but that's just purely my sub-comment. I'm mostly talking to myself here. I'm still thinking about this. Anyway, for A equals 8, what do we have here? No stable structures, okay? 56, 57. Let's take a look at it. Why? Why don't we have stable structures? Well, because they look ugly, I guess. I mean, he makes some considerations here, but then again, I don't really want to look into it into too much detail. But for example, beryllium 8, you can see you can make it from 2 alphas essentially, right? Or something like this, okay? Oh, yeah, okay. I'm just if I keep reading it, it would take at least a few hours. Anyway, A equals 9. Only beryllium 9 is stable, whereas 2 alphas and a neutron. Page 60. Let's take a look at it. So this is 1 alpha, and 1 neutron in between them. Essentially, it kind of glues them together. So a neutron is essentially a glue. So Burtaev also commented that protons are actually very bad for gluing these pieces together, because again, if you remember, how do we get a proton charge? Is we have the same rotation in the fur coat, right? That's where we get the positive charge, and it kind of destabilizes the whole thing. Whereas in the neutron, we have the opposite rotations of longitudinal and transverse components. And he actually often says, especially when he describes the decays or nuclear fission, if you wish, that the neutron is kind of like a bolt that is kind of screwed, you know, or rather like this thing is screwed onto this bolt and this thing is screwed onto this bolt from the other way, right? And he, for example, describes the uranium decay, uranium fission. Like, why is it so easily achieved by thermal neutrons? Was because there is this screw. I'll show you the uranium sometime later. And this thermal neutron is also, roughly speaking, something spinning, right? And it's the thermal neutron sort of unscrews this neutron, and therefore the two parts can fly apart, right? Because again, we're dealing here with some sort of rotations, some sort of oscillations. So why not describe it something like this, like a very simplified mechanistic explanation? But if you shoot a bullet at a bolt, you can't unscrew it, right? You can maybe destroy it, but not unscrew it. But if you like slowly approach it with a hand and slowly spin it, then you can unscrew it with a thermal neutron, I mean, right? So yeah, protons can't glue alphas together, hence boron 9 is not stable. Then if we have more than 9, we face the radical change in structure with flattening with respect to z-axis. Let's take a look at examples so it would be clear what we're even talking about. Oh yeah, so we have this cross of deuterons essentially, and a neutron on top and neutron on bottom. That would be beryllium-10. Okay. Then we have a cross of deuterons with protons on top and the bottom. That would be carbon-10. All right, and boron, I don't see a scheme here. I mean, I would assume there's one proton and one neutron. That would kind of make sense, right? So, what kind of flattening? Only beryllium-10 is stable, by the way. Again, we can see that. There are neutrons. So these are deuterons, okay? And essentially, this is like 2 alpha particles, right? But they're in this sort of cross pattern. This is, again, some sort of isometric projection. It's actually, this is the same plane. They're in the same plane, these deuterons. Well, anyway, this is Burtaev's idea, how it should look. Then let's take a look at boron-11 and carbon-11, 67, 68. We're gonna accelerate very soon, don't worry. So yeah, so this delta is this cluster of 4 deuterons, okay? We have neutrons on top and the bottom for boron-10 and a proton at the side, and as you can see, its magnetic moment is slightly tilted, actually significantly tilted. And the same here for carbon-11, but we have a, you know, proton instead of a neutron or vice versa. Doesn't really matter. Okay, now let's take, so this delta cluster is why we have this flattening, right? This delta cluster of 4 deuterons forming is what causes this sort of quasi-pancake shape with a hat on top and the bottom, made from neutrons or protons or vice versa. And then we have a incredibly high abundance of CN and O, carbon, nitrogen, and oxygen. And why is that? Well, it's because once you get to 12, so we considered 11 for now. Once you get to 12, you can form 3 alphas, and they form also a cluster of their own, which Burtaev calls trihel, meaning like 3 heliums, basically 3 alpha particles, right? And it looks like page 74. It looks like the, I mean, he depicts it like this, right? But it's like 4 deuterons essentially, and a 1 deuteron in between them, which is kind of shared among all of these, right? Oh, wait, that's not enough particles actually. Let me think about it. Well, it's 3 alpha particles, so it should be 6 protons, 6 neutrons, right? Let me think about this. So why is it arranged in a cross pattern? That's the question. I'm kind of thinking about this. Because this is 4, right? If there's 4 deuterons, what is in the middle? Probably alpha particle, actually. Yeah. There's like an alpha in the center and 4 deuterons at the edges, essentially. But together, it creates like virtual 3 alphas. That's the idea, I think. I've read it yesterday, and it made so much more sense. Today, I'm kind of in a fog a little bit. I don't quite remember. But yeah, essentially, it's 3 alphas, okay? He calls it a Kappa cluster, or trihel again, and he describes how various structures are possible. Again, you can make an alpha and 4 deuterons in a sort of a tetrahedric pattern, or you can have a cross like this, so it would rotate like this around Z, or you can have a flat cross like this, and it would rotate around Z. And he describes different possibilities, and in fact, there is one interesting idea he gives, but only like in passing, okay? He never returns to it. Is that maybe the nuclear structure can actually change even for the same nucleus, And he assumes that in case of carbon, this is what happens, okay? So he says maybe, like this is the most stable, the simplest one, okay? But he says maybe this structure is realized for carbon, for the nuclei of carbon, I repeat, not the atoms even, the nuclei themselves, in organic molecules. And this one is in compounds like diamond, for example, the tetrahedric carbon. Maybe even the nucleus changes. That's, of course, a big assumption, but it was interesting enough that I immediately noticed it, okay? But that's just a comment. Let's return. Okay, let's just accelerate significantly. Okay, so we have this K cluster of alpha plus 4 deuterons, essentially virtual 3 alphas. So this is what we already talked about. And again, he actually literally says, this is my assumption. Okay, so he doesn't say why, he just says maybe it's the case. So 12 boron and nitrogen don't have enough protons or neutrons to realize such stable structure. Page 76. So this would be boron 12. Wait. No. B is boron 12. Where is it? Well, it should be this one, right? Well, it looks pretty ugly, right? 12. Oh my god, it's pretty confusing. Well, let's just settle for they can't realize such stable structure, okay? Like, I just don't want this video, like, we could have looked into all of these small details, but I want to communicate the basic idea, okay? So let's just take a look at some others. Like, this is A13. This is, again, this Kappa cluster of 3 alphas, essentially. Then we have, oh, sorry, I shouldn't have opened Discord. Well, we're just gonna ignore it, okay? It's not gonna be a big deal. 14, 15, 16. Well, let's just skim through it. So that would be 14, some possibilities here. Once again, Kappa cluster is 3 alphas. That would be 15. And I think that the box is a proton and a circle is a neutron. It could be vice versa, actually. I mean, you can probably count, like if there's 4, probably the circle is a proton, it seems, right? Circle seems to be a proton. Never mind. Not the circle. I mean, obviously, it's like a ball. Okay, so 16. When we go to 16, what happens? Well, not a whole lot, honestly, right? Though, you can actually form an alpha from these guys, right? Is there an alpha here somewhere? Yeah, for example, the excited state of oxygen is a Kappa cluster, 3 alphas plus 1 more alpha, right? So, again, look at all of this. 700 pages of this stuff, 750 actually. You don't expect me to lecture you onto this. You'll have to read it. You'll have to read it somehow through a translator or something if you're interested. But I think the general idea would be good enough. Then once we reach alpha 20, sorry, not alpha, A equals 20, we reach next big transition where we can form 5 alphas. Therefore, something like alpha, kappa, alpha is possible, right? Again, kappa is 3 alphas. And we can get this cross of 3 alphas. We get 20 neon, right? Let's take a look at it. This one. And then again, we can have some excited states where it's not the case, right? Where it's rearranged so it can decay and blah, and blah, and blah, or rearrange backwards. Then, once we reach 24, we can form 2 trihales or 2 kappa clusters with 6 alphas total. Then we get to magnesium 24. with a bunch of nuclei in between them. So this would be magnesium 24, the main state, very stable, right? Obviously. Then once we get to 28, we can insert one alpha in between them. That would be, how do you call it in English? Silicon, yeah. 133. Okay. We're accelerating, boys. So this would be, again, silicon, sorry. I keep remembering the Latin name, silicium. Anyway, kappa, alpha, kappa. So the cross of 3 alphas on top of alpha, and then again, a cross of 3 alphas. Then once we get to 40, we can get 2 pentahales, where 1 pentahale is, again, 5 alphas, obviously, so 10 alphas total. Then we get to calcium 40. So here depicts 1 pentahale, 1 cluster of 5 alphas as He, or Chi, I guess, is read in English. It's a Greek letter, right? Wait, what's the page? Actually, I don't have the page here. I have to find it. Okay, that's 32. Where do we have calcium? Chlorine. Argon. Well, this is an excited state. This is the base state. So this chi, or chi, I don't know how you read it in English, it's a Greek letter, is again the cross of 5 alphas, okay? So you have 1 alpha at the center and 4 alphas at the sides, like a flat cross. Just like we saw with trihale, but now it's like actual alpha particles, right? 5 of them. This would be this chi cluster. Again, kappa is a cross from 3 alphas. Again, sort of a virtual, right? Virtual one. And this is just a block of single alpha. So, yeah. And actually, that concludes book 1 in my notes. Well, all right, let's take a look at book 2. So once we get to 44, we can form, again, kappa, chi, kappa, or 11 alphas total, right? So we have 5 here, 3 here, 3 here. So that would be 11, 5 plus 6, right? That's titanium, 44. 237, book 2, page 37. Oh, we're almost there. Actually, you can see the various excited states, various isotopes, and their structure, right? And all the parameters. It's pretty crazy. Pretty crazy. So where do we have titanium? Wait, where? 37. Oh, okay. So these are the main, like, crucial points that we've considered so far. So helium 4 alpha particle, big deal. Carbon 12, trihale, 3 alphas, right? Magnesium 24, 2 trihales, 3 alpha crosses, right? 6 alphas total. Then argon 36 is like a very long, well, rather long structure of alpha, kappa, alpha, kappa, alpha. So every kappa is 3 alphas in a flat arrangement. Calcium 40 is 2 chis, where chi is a 5 alpha cross. Then this is titanium. So kappa, chi, kappa. So as you can see, it's not like a very linear progression, right? Like it changes along the way. And this change is what drives the periodicity of the table, of the periodic table. So you have like different groups of elements, because they look differently, right? And we'll return to this at the very end. Then we have chromium. I think it's chromium, right? 48 with alpha, chi, chi, alpha. And iron 52 with chi, kappa, chi. And by the way, when we're talking about these things, you have to also remember that you can also always add neutrons pretty much everywhere you want. So he actually talks about what he calls, Burtaev talks about the so-called FGH structure, where F is, well, you may roughly treat it as frame. So this is the frame here. It's the main block, right? But on top of this frame, or rather to the side, this is the F, right? But on top of it, you can have a hat, so to speak, and that would be H. And at the sides, you can have G. I don't know how to translate this. It's just G. So G would be additional neutrons or protons that you put at the sides. It's usually neutrons. Because again, protons, they are not very good at connecting. So G things at the sides, H things at the top, and or bottom for that matter. And F thing is the main thing. It's the frame, right? So that's FGH structure. Just remember that you can always add G neutrons around, or sometimes even protons, and H neutrons and protons on top and the bottom to progress from one element to another. That's what I mean. All right, so pretty good table. Then, where are we? Well, I think I just got depressed and I just kind of summed it up, right? So there is a periodic table, but I don't want to show it to you because it's incomplete. Okay, I'll show it to you just for the sake of completeness, but it's incomplete. Oxymoron, okay? So this, I'm not gonna comment on this. I'll comment on the complete table rather. But this is the first nucleids, whatever. The first elements, all right? And then the rest of the book is like beta decay, scattering, collisions, like all kinds of descriptions of all kinds of things, okay? All of this is experimental data. All right, book 3. We may get a Xi cluster, which is 9 alphas, okay? Let's take a look at it. I mean, there's nothing to look at. It's just 9 alphas. It's a cross of 9 alphas. So 1 alpha at the center, and at every one of 4 sides, there's 2 alphas attached to it. So when we get over 76 or more, we can get this structure. For example, strontium 76. It's Chi, Xi, Chi, I guess this is the Greek letter. Chi, Xi, Chi. I don't even have a page here. Well, it's too flat. It needs more neutrons, right? That's why strontium 76 is not something you usually encounter, okay? And other similar nuclei, let's take a look at them at least. So again, this Xi is 9 alphas. This is what, 5, 7? I already forgotten. 5 alphas, I think. That would be 9 alphas, 5 alphas, 5 alphas, and there's just neutrons or protons. So zirconium, molybdenum, blah blah blah. Yeah, I don't even know the names of these elements in English, so never mind. Ytterbium or whatever, zirconium, I think. Is it zirconium? I don't know. Sorry. And again, a periodic table 163. That's a continuation, right? So from the first book, and a brief description of structure. Some elements, book 4, page 10. Where's page 10? Okay, well, here are some elements. This is cerium, I think. Some of its isotopes, right? This is samarium, I would guess. So once again, Xi, it's actually written here. 13 alpha, Chi is 5 alpha, and Kappa is 3 alphas, right? So you get these sort of structures. Again, we kind of require the symmetry along z-axis. That's why they are so, well, at least somewhat symmetric, okay? But you can see in some cases you get like slightly skewed structures, etc. And then the periodic table, page 50. Take a look. That's a continuation again. I'll show you a bigger table and try to explain what it means. Then we get to Zeta cluster, which is 13 alphas. Actually, wait, I think I've already shown it to you and misnamed it. Let's return. so this is Xi. Wait, this is Xi. Xi is 9 alphas. Yes, this is Zeta. It's 13. Yeah, I confused the two. Sorry, the letters are pretty similar, right? So 9 alphas is Xi according to Burtaev. It's his terminology, obviously, his nomenclature. So it doesn't really matter, okay? Once you understand that it's 9 alphas, it doesn't matter which letter you use to describe it. And now Zeta is 13, yeah. Sorry. Yeah, this is, we talked about this already, how thermal neutron might be a wrench which sort of unscrews the uranium. So let's take a look at uranium decay. I think this is exactly what is described here. So why does it have two peaks? So this is the mass of the fragments of decay, right? So one fragment is lighter, it's like 95, and another is heavier, it's 130, 140 roughly, right? Why is that? Okay, this is the probability. So the most probable decay is like that. One fragment like 95, another is 130 something. Why is that the case? Well, because actually I'll need to look into structure of uranium. Is it somewhere here? Did we get to uranium here? I don't think so. Well, too bad, actually. How am I gonna even explain this to you? I may have to cut the video while I will be searching for it. Oh, wait. This is plutonium. Good. This is uranium. Or at least, some isotopes thereof. Again, it's not all, it's just F, right? We have G around it and H on top at the bottom. At least, I mean, for certain isotopes, you may need it if you don't have enough neutrons or protons in the F itself, right? So there is one neutron hanging around somewhere here, kind of gluing those two symmetric pieces together. So this is uranium. And the thermal neutron, what it does is it unscrews, for example, this lower part of 13 plus 5 from this one. And that's how you get asymmetric pieces. And actually, Burtaev makes a lot of calculations for not just uranium, but other elements and many other isotopes. And he gets the correct peaks. Like you may say, well, why wouldn't it unscrew it right in the middle? It's actually a good question. So my answer was, I don't know. But in this model, it unscrews it like this piece from this piece, and you get the correct distribution of the parts. Maybe this piece is just more stable. I don't know. Like, you'll have to look into details. But like provisionally, the initial idea would be that let's unscrew right in the middle. I would agree with that. But maybe that's not how it works. I mean, apparently that's not how it works, because you won't get the two peaks. But if you unscrew here, so you divide this wider part from this upper part, you get the correct distribution of pieces. Okay. Yeah, so this would be kind of the end. Let's take a look at the periodic table. So it's on the website. I'm obviously linking this all. So what do we see here? Well, what is this theta group? So it's rearranged with respect to the usual periodic table that you may encounter in textbooks. So theta means, roughly speaking, pancake-shaped frames, right? So these would be like these. For example, remember calcium, it had two like flat crosses on top of each other. Magnesium also was what, 12. It means how many alphas we have? 6 alphas, right? So that would be two stacks, the two crosses of 3 alphas on top of each other. And here we have 10 alphas, so that would be 2 crosses of 5 alphas on top of each other. So that would be like pancake shaped, at least these. And then you keep adding stuff. So you add 1 proton, then you add another proton. You can already form an alpha here, right, with 2 protons. then you add one more, and you form two alphas, and then you add two more, and you get to a trihel, right? The stack of three alphas. That's how you transition to the next group. So this is kind of like the transition zone. By the way, notice how technetium and promethium are unstable. Of course, manganese is stable, but still, it's quite interesting that you get these two unstable elements sitting right in this transition zone. What is this? I don't even know what this letter is. Honestly, I think it's also Xi, but a capital one. But what we are interested, why he calls it that, like theta, is because it's fat at the center, at the equator, right? So these are sort of pancake shaped, and these are hourglass shaped. So in the middle there is a thin bridge. It's like a dumbbell, you know, like a big piece on top, big piece on bottom. Which are roughly symmetric, roughly only, okay, and a thin bridge in between. So, for example, uranium we just saw, right? This structure. That's what we call. I guess it could be Zeta actually. I don't know, or Xi. It doesn't matter. So these are pancakes, these are hourglasses, and this is delta. Well, you remember that it started from a trihel, right? From the three alphas, which is carbon. Well, in general, these look like kind of like, I don't know, cylindrical, I guess would be the best way to describe them. Like not too fat, not too thin, just cylindrical. Maybe barrel shaped, something like that, you know? So this is his model. By the way, I saw in some of his lectures, aluminum was placed here. So it's kind of, don't take it too literally, all right? And once again, we remember this principle that he said, that each nucleus is unique. So you can't really judge the structure just by the position, but some main properties can be judged, all right? And in fact, some physical properties, according to Burtaev, physical properties of elements actually follow from the nuclear structure, because he actually never considers in any of his books the electron structure, and therefore like chemistry is out of limits for us. But even the nuclear structure, according to him, can give you an idea of the physical properties of bodies, not bodies, like what's the word? Matter is not the word. Materials, I guess. But there is another word which you probably remembered, but I can't. Anyway, so properties such as, notice how there are no lanthanides or actinides, right? Which are present in vanilla periodic table. By the way, they were never present in Mendeleev's table. They were added later. I mean, not the elements themselves. Some of them were known to Mendeleev. Maybe actually many of them, but he didn't depict them as... if you look at the modern periodic table, it's absolutely wonky. Like, it looks very, very bad. They usually, like, to hide it, they stuff all the actinides and lanthanides in a single spot, right? Here you don't see this. I think it's very good. And then again, this essentially a hypothesis that physical and chemical properties actually directly depend on the structure of the nucleus, such as, and he actually gives some examples: ionization energy, electron affinity, spectra of excited atoms, or Grotian diagrams, X-ray spectra, radii of atoms, polarizability, compressibility, melting point, boiling point, heat capacity, thermal conductivity, density, maximum magnetic moment of an atom, thermal expansion coefficient, electric resistivity, magnetic permeability. It's pretty crazy. Like, if you look at resistivity, for example, you can see that all the good conductors are here, right? We have gold, silver, copper, aluminum. Again, sometimes he puts aluminum here, actually. I don't really know which one is correct, so to speak. Again, since it's so quite arbitrary, again, like, probably since it doesn't have too much nucleons, right? You can treat its structure, describe it as this or as this. I guess there is ambiguity of this sort. Anyway, let's finally conclude. It's been pretty long, right? To conclude, atomic nuclei must have structure. The structure is what determines their properties. The structure is unique for every nucleus. So given some A and Z, you have this structure or that structure. And it is built on the basis of smaller structures. Specifically, alpha and deuteron are the main ones. And the clusters thereof. Of course, when we talk about the E.th.ph, you can always sprinkle G, neutrons or protons around. You can always sprinkle H, neutrons or protons on top or the bottom. And then again, this interesting hypothesis that perhaps the structure can even change for the same nucleus. I haven't heard it anywhere, but I think it's very interesting. Like, that really makes you think about things. Because why wouldn't it? Good question. Good question. All right. Well, I mean, this video was so long, I'm really tired right now. So let's just summarize briefly. Unfortunately, as a theoretical physicist, I'm very depressed by all of this, because I just looked into these 700 pages and I realized that really, probably, you'll never be able to come up with some simple theory which would describe it. So my summary is actually very dry. It just says there is no nuclear theory, period, right? And it is the case. There is no nuclear theory. We have only models of varying degrees of accuracy and vagueness. In fact, I was thinking about it just now when I've written these notes, and I thought, like, you can probably even introduce, I mean, it's obviously a joke, some sort of a uncertainty principle for accuracy and vagueness, right? Like the product of accuracy and vagueness is constant for any model of atomic nucleus, right? The more accurate your model is, the more, simpler your formulas are, the more vague your model should be. And vice versa. Or rather, sorry, okay, just forget. Well, I just thought, Burtaev has a pretty vague model, but it describes pretty much everything, right? But if you have a model which is like a simple law, it would not describe a whole lot. That's what I wanted to say. Hopefully it made some sense. Yeah. And one interesting, again, takeaway is that we can actually forget the electric charge and use alpha instead. And then the electric force would look very easy. It would look just alpha, not alpha particle, alpha the number, fine structure constant, times h times c divided by distance squared. And you don't get any Coulomb constants, you don't get any crap like this. This is the electric force. Right? There's no electric charge in it, as you can see. Alpha is a dimensionless constant. This is Planck's constant, speed of light, distance in meters. Nothing else. Highly recommended. Maybe we try to fix electromagnetism first, like this. Because again, what are nuclear forces? There aren't nuclear, there's no such thing as nuclear forces, right? There is magnetic force, maybe, probably, no, magnetic force again is a far field approximation of some sort of interaction within substance. What kind of interaction? Well, we have to figure it out somehow. But in terms of nuclear theory, there is none, unfortunately. There is hope that with this first approximation to the nuclear structure that we have in Burtaev's model, maybe we can develop some nuclear theory at some point, but it's gonna take a while, as you can see from the amount of data that we need to describe. By the way, honorable mention, I'll probably finish on this. My friend E.th.ph develops his own model of structured nucleus. So check it out, please. I'll probably link something of his in the description. He has written a book relatively recently with some colleagues, Andreas Otte, Jan Emming, and some others. So yeah, honorable mention. Anyway, that would be enough.
Thank you for watching. The eons are closing. If you wish to support me, please consider joining my Patreon. That is patreon.com/philosopher. See the link in the description. Or if you have a scientific theory of your own and you'd like my help in developing it, please join my alternative science coaching program, also available through Patreon.